morning. Hope you all had a relaxing weekend. It was nice, sunny yesterday. And today as well. All right. And good morning, everyone. Happy Monday. One more week of online classes, and hopefully we'll be having classes on campus on Monday, next Monday. As soon as I receive information from the department, I will send you an email, or Miss Minion will send you an email about the update. But as of now, we will be moving to campus on next February 15th. But if something change, I will definitely let you guys know. Any questions before we finish our topic 2.4? We kind of completed except one concept. If you have any questions, let me know. I extended your homework due date, so make sure that you work on this homework assignment. And there is one more on chapter 2, and then there is a quiz. And you will have your first test next week, which is on chapter 1 and 2, and we will have review sessions for that as well. So far the test will be on campus until unless something will change. All right, so let me quickly go over what we did in the last class. We talked about least square regression, and before talking about the regression, we talked about correlation. And then before correlation, we talk about scatter plot. And before scatter plot, we talk about quantitative variables. So when we need to look at the relationship between two quantitative variables, or you can say numerical variables, we make a scatter plot to see if there is a relationship going on or not. If that relationship is linear, we say that there is correlation going on. Once we know there is a correlation, we can make least square regression line, and using these lines, we can do the prediction. And again, when we are saying prediction, we need to know what we are predicting. So when you make a scatter plot, you have two variables because we are talking about relationship. And for the relationship, we work with bivariate data set. We have two variables. We look at the relationship of those two variables. If that relationship is linear, we say that we have correlation. And then in the correlation, we need to know which one, we need to know two variables. One variable is explanatory and another variable is called response variable. If we know which one is explanatory, which one is a response, we make this, plot this on X and plot this on Y. But if we do not know, if the distinction does not exist, or we cannot distinguish between explanatory and response variable, we can use any axis to use response or explanatory variable. Once we see there is a linear relationship going on, then we use least square regression line to predict the value of y on x. Or in other words, you can say that we need to check the response using explanatory variable. So when we are predicting or looking at the value of response variable, the distinction between response and explanatory variable is necessary or must. So once we know which one is explanatory, which one is the response, what we are predicting, then we can do least square regression line and predict the values of y on x. And we use the equation for the regression line. This is the equation. And when we predict, we put a hat on top of our response variable. This is my y-intercept, basically where the line is touching on y-axis when my x is 0. And this b1 is your slope, and this x is your explanatory variable. And this y is the predicted value of your response to it. So you need to know what is the equation of the line, what is the predicted value or predicted equation of the regression line, what are these individual, what do we mean by this, if we have this value, what do we mean by this. When we talk about the slope, slope can be both positive or negative depending upon which direction is your linear line, which direction is your correlation. If you have positive correlation, then your slope is positive. If you have negative, then your slope is negative. This equation is same as what we have done previously. So you can use any of that. In the slide and book, we are using this, but you can do anything that is more meaningful to you. And then we also learn how to calculate the value of slope and intercept. So if we are looking at the slope, what do we need to find? When we are looking at the intercept, then we need to use the slope here. So first thing, calculate your slope. And R is basically we use for measuring the strength of the linear relationship, correlation coefficient. This is the standard deviation of Y. This is the standard deviation of X. This is the mean of X. This is the mean of Y. And this slope comes from here. And then you can calculate Y-intercept also. When we use the least square regression line to predict the values of y, least square regression line always passes through the mean of x and y. So mean of x and y is always on your regression line. So when we say regression line, there are a few things that we need to be careful when we work with correlation, when we work with regression. For regression, we use this r squared. It tells us the usefulness or how good fit that line is. R square and R, we use this for correlation, this for regression. But if we know one, we can calculate other. If we know correlation coefficient, we can calculate R square by doing the square. And if we know R square, by doing the square root of R square, we get R. The only thing is when you do the square root, you get both positive and negative value. And when we have positive and negative value, you need to decide which one you want to work with. You are going to work with positive or negative. So look for the clues or look for the information that is provided to you in your question or what you are working with. So if you see the regression line is negative, then you know that your slope is negative, then take the negative value, otherwise take the positive value. So this one, negative and positive, depending upon what your correlation. Either look at this scatter plot or look at the slope. So slope and correlation coefficient, they share the same sign. If one is positive, other is positive. One is negative, other is negative. And again, let me quickly go over this part. So here, this is what we just talked about, that regression line is a model for linear relationship in bivariate quantitative data. Again, you used to predict the value of y for a given value of x. Predicted value of y had this in this symbol, and that's how we calculate our slope, y-intercept. And then you can use your calculator to find that as well. Calculator, both equations are given. In calculator, when you use, this is also there, and this equation is there. So take a look. If you're working with this, then this is your slope and this is your y-intercept. But if you're using this equation, this is your y-intercept and this is your slope. So it changes. So make sure when you look at the line using the calculator, which equation you are using, accordingly, you can pick your slope, because it will give you the value of what is the value of A, what is the value of B, what is the value of R. You know that you are talking about correlation coefficient. A and B is your slope and intercept. If you took this equation, A is your slope. But if you work with this, then Your b is the slope, not 8. So it will change. And some facts about least square regression line. Distinction between explanatory and response is must. Least square regression line, what do? They minimize the sum of the squares of the residuals. And last time I think we talked about residual. The residual is the difference between your observed value as well as the predicted value. Let's say this is my observed value. But when I fit a line, this is my predicted value. So this is my observed value. This is my predicted value. Residual is the difference between this. How much is this? This is the residual. And same thing if you have a observed value here, then this is your observed, and this is your predicted. So this is your residual, y minus y hat. So it can be positive or negative depending upon where is your observed point. Is it above the line or below the line? And here is this. Residual is y minus y hat, your observed value minus predicted value. So vertical distance between the actual data point on the scatter plot and the predicted value of y on the regression line. So this is your actual and this is your predicted. And this is your residual. The difference between y minus y hat or observed minus predicted. And again, making residual plots is hard manually. We use technology to work with that. Slope of the regression line has the same sign as R. Change in 1 unit of X means change of B slope units in Y. So if we have, so when you are trying to predict this, your slope and y-intercept is fixed, because if you have this line, so you have a slope and where it's intersecting at y. So as you plug the value of x, the value of x 1, 2, 3, or whatever value of x you have, it multiplies with the slope and then it adds with your intercept to give the predicted value of y. If your slope is positive, the values will increase. If the slope is negative, so you are going to subtract this value from your y-intercept, so it will go down. And again, it depends upon what kind of, what values of x you are plugging. And points x bar, y bar is on the regression line. And I have one more document for my other class about the least square regression line. I will upload that also. Again, if it is not from your book, it will not say chapter 2, but I will upload under chapter 2. So if you want to use it, you can use it. That information, if you don't want to use it, don't use it. It will have different chapters marked on that, because it is not from your book. But it is about least square regression line, and there are some examples. We will upload that. If you want to use it for extra help. If not, that is totally fine. You can use your book, you can use your lecture slides, and you can make your own notes. And by the way, at the end of each chapter in the book, right before the exercise, there is a page. It says summary. And when you look at that, it talks about all the important topics, or then you can see the definitions and the formula. So if you want to use that as a note, as like what are the topics that I learned in chapter 1, what are the formulas, and make a note to yourself, then that summary part is a good part, because it talks about everything, all the formulas. And I'm not suggesting just look at that part. You can look at everything, but that's a quick concept check kind of thing that you can go over. Okay, I got this concept, I understood this. Oh, this I still need to work on. So I can go back to the book, or you can come to us, or you can read the notes, and that will help you to understand all the chapter concept. R squared is a fraction or proportion of variation in y explained by the regression line of y on x, explained by its linear relationship with x. And technically what R squared does, it tells us the success rate of the regression line for prediction. How good fit that line is for prediction, we get using R squared. Influential observation, again, when we talk about regression line, and we make a scatter plot. Not necessarily our scatter plot is very clean and we can just fit a line inside. Sometimes you have outliers on the extreme ends or in the middle or on the side. So you need to take care of those outliers also, because those outliers can change the value of your R square depending upon where that outlier are. Some outliers does not change anything. So some outliers change your value of R squared drastically. And when they change, we call them influential observation or influential outliers. Regression line and R can be strongly affected by outliers. Influential observation usually represent outliers. If removed, the calculated value in the regression line will change a lot, or not. If not a lot, it will change, then it is an influential observation. And outliers in x direction more influential than outlier in y direction of the regression line. And if outlier is in the same direction, let's say you have this, and then you see there is an outlier here. So then you know that if you're trying to predict a line, it will be in this direction because I see the outlier is here. Not necessary if it passed, but I know that it will be somewhere. So outliers in the same direction strengthens your correlation. Cautions, or you can say the precautions or the things that you need to be careful when you work with correlation and regression. Correlation and regression line for linear relationship only. No matter how strong your other relationship or association is, we cannot talk about correlation and regression because we are talking about linear relationship. Plot your data always before you use it. Whatever you have your data, what data set you have, first you plot it, and once you plot it, then you see if you can see a linear pattern. And again, when you use the software, you can see that. You can use that if there is a correlation going on. What's the value of R? You can see, try to fit a line and see if that is fitting in it, or is it giving me something else? Am I getting a circle, or am I getting a curvature, something other than linear? Then I'm not talking about correlation. And if I'm not talking about correlation, no linear relationship, then definitely I cannot do my regression line inside that scatter plot. Extrapolation happens a lot of time when we try to predict something for outside our overall pattern. And I think we did an example about the height in age. So if we're trying to predict the height of a child, 1 year, 2 year, 3 year, and keep on going, and then 10 year, we see that the chart is going up. Can we predict the height at the age of 30 years or 40 years? And can we say that it will keep on growing as we keep on moving? So at 10 years, 20, 30, like if I keep on going, so will my height will be somewhere here. And again, when we are talking about prediction, we need to be careful what we are predicting. If something is outside your overall range, it will give you false values or false value of R. Or so that is called your extrapolation. So extrapolation is use of regression line to predict Y for values of X far outside the observed value of X used to calculate the regression line. And we know that at certain age our heights, we stop growing, our height stops. So we cannot predict our height at the age of 50 or 60 or 30. So when we go to the doctor, they make a chart for the newborn baby. Okay, 1 year, 2 years. So looks like at the age of 16, this baby will be at this height. So again, they are predicting, and sometimes it's not accurate or exactly the same that they mentioned, because again, everybody is different. And when we are saying that they are predicting, there are so many factors in between that. And I can give you an example about my kids. I'm 5 feet 5 inches tall. So when I had my first daughter and I took her to the doctor, and then she made a graph, and then she's like, oh, she will be at the age of 16, looking at your genetic history, your your family, your husband's family, and all that component, she will be like if not much, at least 5'5" or 5'6". And same thing with for my other daughter. But now my daughter is 24 and her height is she's 5 feet 1 inches. And if looking at the chart, I cannot say at the age of 30 she will be 5'5". I know that she's not growing anymore, so her height is what it is. So just one thing, extrapolation. And second thing is there are so many other factors that are not in your study. You are just talking about age and height, but there are so many factors in your study that are affecting your response. And then we are calling that lurking variables. Or you can say that those lurking variables are also called as hidden variables. So the variables, they are not in your explanatory and response. They are neither in your explanatory, not in your response, but they are affecting your response variable. And then we call them lurking variable. So lurking variable is not among the explanatory or response variable in the study, yet may influence the interpretation of the relationship among the variables. And a common example that you can take as smoking and lung cancer. So if we are taking smoking as X variable and Y variables like how many subjects will get lung cancer because of smoking, so we can make a chart and we can make a scatter plot and look at X and Y. So if we can keep smoking here and lung cancer here, and we know that smoking and lung cancer are associated, or you can say they are correlated, you can see a linear relationship. But again, when we are talking about smoking and cancer or lung cancer, these are the two variables that we are working with, but not necessarily the result that I'm getting on Y is just because of X. It can also depend upon my family history. It can also depend upon other factors I have, what other diseases I have, or my eating habit, or some other things also. It's not just because of smoking and that smoking is causing cancer. So again, when we are talking about association or correlation, there is a correlation going on. But again, when I'm saying the response variable that I get, the value of response variable, not necessary that I'm getting it because of explanatory. There are some hidden variables and there are some mixed variables. So there might be, like I'm saying X, there might be two explanatory variables, height and age, or something else. So if I'm using 2 or 3 explanatory variables, I'm not sure the result on Y is just because of X1, X2, X3. So then I can say that the result is because of the mixed variable or mixed response. Then we call them confounding variables. So let me write here also. Confounding variables. So when we are saying lurking variables, again, we need to be careful. Lurking variables are the hidden variables. They are neither in your explanatory nor in your response, but they are influencing your response. And when we are saying confounding variable is basically when I'm using more than one explanatory variable, or if I'm working with the explanatory variable and looking at the response variable, the response is not just because of X1, just because of smoking. It can be from other variables also. So then I'm talking about my confounding variables. Association, and this part is really important. Association or high correlation does not imply causation. So we are saying that there is an association or there is a correlation, high correlation. The value of R is almost as close as close to 1 or -1. But that does not say that there is a cause and effect relationship going on. So association or high correlation does not imply causation. So if there is correlation, we cannot say that there is a cause and effect relationship going on. There is a correlation. So I can relationship, one going up, or one going up, other going down. But that does not mean that there is a cause and effect relationship going on. So the correlation may be coming from an underlying factor driving both conditions. Even when direct causation is present, it may not be the whole explanation for the correlation. So keep a note to yourself that no matter how strong correlation is, that does not imply causation. And here are the examples. So make sure you go over those examples and it will help you to understand how to calculate B0, how to calculate B1, what is the value of R, how to use that. So that will be helpful. And let me go back to our slides. So this is what I just explained. Causation and cautions about correlation and regression. Correlation does not imply causation. Now we are going to talk about our last topic, 2.6. So you will be good to do your homework assignment. And I think I showed you the least square regression document last time, how to use that in your homework assignment. Did we talk about that last time? If not, let me just quickly go over this part. I think I did, but let me just quickly go. So if you have a scatter plot, you use your data set, and let's say you put this data set in Minitab or excuse me, Excel or any other software, and you get a scatter plot. Once you get a scatter plot, like you get an idea that there is some correlation going on, and I can see the form, direction, and strength, and it also gives me the output. Once I get this output, and by the way, this document is on your Canvas also, so you can take a look at there. So if you have something like this, like when you work on that and you get this, how do we read those, or how do we read this results, or how do we read this table? So when you look at the table, on the top you see an equation. So it says that fat gain is this. And where is this equation coming from? So let's go to the table. So when I go to the table, I will see here R square. So that is my value of R square, how good fit my least square regression line is. And then you have R squared adjusted, R squared predicted. So just leave that, just look for the R square value. And then come to this coefficient. When you go to coefficient, you look at term, constant, and this NE. So when you look at the constant, this constant is your B0. This is the value of your B0. And this NEA, when you look at your data set, this is my explanatory variable. So if this is my explanatory variable, this is my X. If this is my X, this is my constant, what is my Y? So when I go back to my table and then I see what two variables I'm working with, if this is my X, then definitely this is my Y. So my explanatory variable is NEA increase, and what I am looking for, or what I'm looking for the predicted value, that is my fat gain. So my response is this. So I'm looking for fat gain. And if you look at this equation just talk about this. Fat gain is your Y hat, and this is your B0, and this is your B1. And instead of writing X, I'm writing what is my explanatory variable, NEA increase. So go back to your table or your data set, and then you do that. So in your homework assignment, there are questions, so just don't pick X. You know what your X is, so use that value of X. Most of the time when you get this result, this equation is provided to you in your result. But again, in your homework assignment, it's checking that if you have this output, how do you use this output to make this equation? So read what is given to you, and then find your explanatory from there, look for your response. Once you make the equation, if let's say the question is giving NEA is 2, what is my fat gain? Can I calculate? Yes, I have this equation. So instead of this, I multiply this with 2 and I do my math to get this predicted value of fat gain. So again, there are a couple of questions in your homework assignment. It gives you the value of R squared. So when we are saying the higher the value of R squared, the better the fit it is. The lower the value, it's not that good fit. Because R squared tell us how good fit your regression line is, or usefulness or success rate of your prediction value. And these results are from the Minitab, and these in your homework assignment you have very similar question from Minitab output, so you need to know how to read those. And again, the information that we just talked, what is R square, what is R, B1, B0, if I know one, how can I find my other one? Look at that one. And there is another example, so look at this example and try to look for, and again, you don't have to solve anything for this. Every single thing is provided to you in this table. So read the table, make the regression line, look at the value of R square, and then R square values in decimals. So convert into the percentages and see how good fit that is. What is your response in explanatory variable? Then try to make the least square regression line using this information, and then use what is the value of R and what do you say about that. So work on that part. So I guess we are good with up till 2.5, but if anyone has any questions about that, please let me know now or later. Okay, so if no questions, we still have 20 minutes. So let me just quickly start 2.6, which is the last topic of our chapter 2. And your second homework assignment is on this topic. So first homework assignment 2.2 to 2.4, we kind of finish every single thing. So you should be good on doing that. And I saw this morning that most of you have taken your first attempt on that particular homework assignment. So I hope now the rest of the concepts are also clear, and you can take your second, third, or whichever attempt you want to do. If you're satisfied with your first one, you got 100, you don't have to do it, or whatever score you get and you're satisfied, you're fine. But if not, I'll suggest you to spend some time and do that. 2.6, data analysis for two-way tables. In the beginning of the chapter, we talk about that when to use or what to use when we are looking at the relationship of the bivariate data set. So when we know our bivariate data set is quantitative, when we talk about numerical variables, then we use correlation and regression. But when our data set is categorical, we can make scatter plot, but that scatter plot does not give us any relationship between two categorical variables. So what to do? Then we use two-way tables to look at the relationship between two categorical variables. So when you start with numerical variables, your first point is make a scatter plot. When you work with categorical variables, your first step is to work with two-way tables. And when we talk about two-way tables, when we make a table that has two ways, similar like in simple word, rows and columns, then we are talking about two ways. One way is either I'm going through the row, or the second way I am looking at the column. And again, as I mentioned, like most of the words, very simple, make perfect sense if we just break the word. So I'm looking at the table that has two ways to work with. Either I can work with row wise or column wise. So I'm talking about two-way table. Marginal distribution and conditional distribution. Again, when we say the word margin, what does margin means? Anyone? So when we are saying the margin of this table or the margin of this paper, so I'm talking about the corners, right? If this is my sheet of paper and I'm looking at the margins, so margins are this, the boundaries or the corner. So again, when we say marginal distribution, we use a two-way table and we look at the margins of those two tables. And then we are talking about marginal distribution. When we say conditional distribution, again, the word conditional. So when we are saying that we are looking for a distribution where some kind of condition is applied. So we are using some condition, and then we are looking at the value of that condition and then finding the corresponding distribution. Then we are talking about conditional distribution. Simpson's paradox. Simpson's paradox is an important, you can say that application that we use. And again, Simpson's paradox will make more sense once we understand what is marginal and conditional distribution. But let me just explain in like two sentences, and then we will do it with an example later on. Excuse me. So Simpson's paradox is actually means that when we work with a two-way table, when we work with two separate two-way tables, we get results. And when I combine that two-way tables, my result is reverse to the result of what I have in individual two-way tables. And I think when we do example, let's keep it on hold. When we will do examples on this, then it will make more sense. So first, let's talk about marginal and conditional distribution. Questions up till this point? Okay. So let's quickly review what we just did. The categorical variable places individual into one of several groups or categories. We learned that in chapter 1. The value of categorical variables are labels for the different categories. And again, when we are doing the categorical variable, we use pie chart or bar graph. And the order of the categories does not matter. You can move from any order from 1 to 5 or 5 to 3. So you can just swap around. It's not going to change anything. The distribution of the categorical variable is the count or percent of individuals who fall into these categories. When the dataset involves two categorical variables, we begin examining the counts or persons in various categories for one of the variables. So we are talking about categorical variable. We have the result. We have the data for categorical variable. So what's the first step? We make a two-way table. And how to make a two-way table? We'll see how many categories we have and what are the counts for each category. So, and again, we are talking about two-way tables. So we need two variables. And again, when you are looking at the relationship, you cannot look at the relationship with just one individual variable. So two-way tables need two variables. Two-way table describes two categorical variables, organizing counts according to a row variable and according to a column variable. So like how I said, if we make a table, I'll do one variable here and one variable here. So this is my column and these are my row. So when I'm saying row column, so this is any entry here is need these two things, right? Any entry here needs the value of this as well as this. Same thing here and here. When you are talking about this, we cannot get this value until I know the value of this variable and this variable. So we call that this is the value of this particular cell. So this is this cell. And let's say I'm saying x1 and x2, y1 and y2. So this cell, this value is x1, y1. So what is the value of x1 and y1? This cell is representing this. Similarly, if I'm talking about this cell, this is x1 and y2. And then you can keep on doing. So when we talk about marginal distribution, and again the word marginal comes from the word margin, so we are talking about only the margin of two-way table. So that means we are not going inside the cell when we are talking about marginal distribution. Then what we are doing? We are just looking at the outside or the margin of this two-way table. And again, when we do marginal distribution does not tell us the relationship between two categorical variables. It will give us the relationship between the margins with the total, but not the relationship. If I need to look at the relationship between two categorical variables, then I need to work with conditional distribution. But again, either you work with conditional distribution or marginal distribution, you take two-way tables, and then you do marginal distribution first to calculate your conditional distribution. So let's say this is a two-way table, and please exclude this messing up stuff because I want you to explain this part first before you see those numbers. So a two-way table is given to us. It says that young adults by gender and chance of getting rich by age 30. And then I have two variables here. One is gender, young adults, and second is what are the chances of getting rich. And then we label them as female and male, right? So we have female count and we have male count here. So this is the two-way table that is provided to us. Now, the question is asking what are the variables described by two-way table? And we talk about that. What are the variables? Young adults and chances of getting rich. And then you have different categories, and then you can label it female, male, and here almost no chance, some chance, 50-50, good chance, almost certain. So this is the table that is given to us. The next question is asking how many young adults were surveyed. If we are looking at young adult, there are two ways. I know that how many we have. So we are saying that I have these many, right? So you can add everything and you get that. So that is, you will get the total. And now when you're working with two-way table, and next step you have to look for the conditional distribution. The very first step is create an extra row and extra column. And this is your extra row and extra column. So once you create your extra row and extra column, what you do is, and again, this sometimes it's given to you, sometimes it's not. Sometimes you have to create it. So when you create this extra row, and same thing extra column, write this as total like how it is here, and then do the column total and do the row total. And these are your row total. And these are your margins. So now whatever you have, forget about this, whatever you had earlier. Now for marginal distribution, what you are going to do is you will work with only this part and forget about, let me not do this. Forget about this now. You are not using this for marginal distribution. So you are not going inside any cell when you work with marginal distribution. For marginal distribution, you work with either the row total or the column total. And if you're working with this, that means we are having only one value. And then when we are looking for what is the marginal distribution of the female or the male, then you will look for how many female you have and altogether how much. So what's the percentage? You can look at this, divide with this. For male, you can look at this, divide with this. What's the percentage of almost no chance? This divided with this total. And same thing, you can keep on doing. So here you are dividing with the grand total or the sum total when you work with marginal distribution. And again, as I mentioned, we are not going inside the cell. We are just creating an extra margin, marginal row and marginal column. And then we work with that margin row or margin column depending upon what information is given to me and what I'm working with. So here is the definition. The marginal distribution of one of the categorical variable in a two-way of counts is the distribution of value of that variable. And that variable, let's say that variable female or male, among all individual described by the table. So you can say variable, whichever you are looking, with the total or the grand total, whichever make more sense to you. So when you're dividing with the grand total or the sum total with what distribution you are looking for with that variable, that is talking about marginal distribution. So again, when we say we are working with marginal distribution, we are only working with the margins of this table. And these are my margins that I created. Sometimes it's given to you in the table, sometimes it's not. So then always whenever you have a table that is given to you, do an extra step, create an extra row and extra column, and then you can mention that as total, and then do the row total here, row total and column total. And then you can check that when you add this, when you add all these and you add all this should be same. So the sum of the total rows and sum of the columns should be same. And if it's not coming same, then go back and check that there might be some calculation work that is not done correctly. So row total and column total should be same. That's why we put it here as the sum of these as well as the sum of this. So this grand total should be the sum of this and this. And if you're looking for this particular one, this divided with this, or this column divided with this, whichever the question is asking. Persons are often more informative than counts, especially when comparing groups of different sizes. Because if you have the count, if I look at this number, this might not give me a better idea because I'm just looking at these numbers. And percentages are more informative when you say that 194, 233, or 296. When I say 40%, 43%, 29%, the percents give me a better idea instead of just the counts. To examine a marginal distribution, use the data in the table to calculate the marginal distribution of the row or column total. Make a graph to display the marginal distribution. Once you have a table, then you can make a graph and to see what kind of distribution I see. And we are using the same table that we just used. And if young adults by gender, chance of rich, and then you see the total you have, this is the same table that we use in the 2 slides back. So now here, instead of just looking at these numbers, we calculated the percentage. And how to calculate the percentage? 194 divided with 4,826. And then we get 4%, 14.8, 2. And then we can look at. And once we know, and again, we are talking about categorical variables, so you can make either pie chart or bar graph. Again, it adds up to 100%. You can make a pie chart or bar graph. And when you make a bar graph, again, the order does not matter. You can bring this here and this category here or any way you want. And you can examine the marginal distribution of chance of getting rich for each category. Questions? So let me just talk about the definition of conditional distribution and then I'll stop. Like as I mentioned that conditional distributions, we are applying some condition to calculate the value using a distribution or a two-way table. So marginal distribution will not tell anything about the relationship between two variables. If we need to find the relationship, this is the only way we have to work with. So a conditional distribution of a variable describes the value of that variable among individuals who have a specific value of another variable. So conditional distribution tells us that we need to first locate or first look at what condition I am looking for. So when I'm looking for let's say here, if I'm looking for a female and has 50-50 chance of getting rich, I cannot just say this. Then I'm talking, or I cannot say this whole. Female and a 50-50% chance of getting rich. So first I will go to the column female and then 50-50. So where these two meet, so I'm talking about this particular, and I cannot find 696 until I have that condition. And let's say my condition is male and almost certain chance of getting rich. Can I still use this? No, now my condition is different. Male and almost certain chance of getting rich. So I'm talking about this. And again, when I'm talking about male, then what is the condition? Am I looking among the males? If I'm looking among the males, I divide with this. If I'm looking for among the people or among all the people who have almost certain chance, then I'll divide with this. And if I'm talking about the male, almost certain chances among all the subjects in this study, then you divide with this. So now we are talking about three denominators. First, you are looking for the cell. So cell is your numerator, the condition that you are looking for. And the second condition that you are looking, this is what you located. You went in the cell. Now, am I looking for this 696 or female with 50% chance among the females? And if I'm talking about the among the female, how many females were there? Or if I'm talking about among all the subjects who have 50-50 chance, then I'm dividing with this. Or I'm looking at this condition with all the subjects, and all the subjects are this. And again, when we talk about conditional distribution is a little bit work, but as long as you know which cell you need to go and you are looking at the relationship among what, row total, column total, or grand total, then you can do that. And there are not very many, there are not very many. There are not any other example except this in this lecture slide. But again, Stat 108 notes, if you see there are a couple of examples that are solved. And then we will be using these examples in the next class so that it will make more sense. And at this point, I'll stop here. If you guys have any question, let me know. Otherwise, happy Monday. Have a wonderful week ahead. Thank you, everyone.
Thank you.
Thank you.
Thank you.
Are we done covering everything in chapter 2 then?
Excuse me?
Or is there anything else we're covering from